welcome you again to the lecture series of multivariate calculus. So, in this lecture, I will talk about the Euler theorem. The Euler theorem I already talked about in the previous lecture. So, in this lecture, I mainly talked about the Euler theorem of the first order partial derivative. So, what was that theorem? If z is a homogeneous function of degree n, okay. So, z is a homogeneous function and you know how to calculate the homogeneity of the function of degree n with x and y. In x, y are the two independent variables. Then the following equality hold: x del z del x plus y del z del y equal to nz, where n is the uh, degree of the function, homogeneous function. Okay. Now, if I extend this function for three independent variable, suppose z is a homogeneous function of degree n and x, y and w are the three independent variable, then we can say that x del z del x plus y del z del y plus w del z del w equal to nz, where n is the degree of the function. Now, if I want to extend this Euler theorem to the second order partial derivative, so here all the partial derivative involve only for the first order derivative, right? Del z del x del z del y all are in the first order partial derivative. Now, in terms of second order, I can write in this way. Suppose here similarly z is a function of degree n, a homogeneous function of degree n in x and y, then I will get this equality x square del 2z del x square plus 2xy del 2z del x del y plus y square del 2z del y square equal to n into n minus 1 into z. Okay, where this is the second order partial derivative of z with respect to x, and this is the second order partial mixed partial derivative, right? And this is the second order partial derivative with respect to y of the function z. Now, by using this formula, I can derive some result. So, for this, I will take this example. Suppose u is a function that is defined as sine inverse x plus y square root of x plus square root of y, and I have to prove this first. Number one, I have to prove this one: x del y del u del x plus y del u del y equal to half tan u, and the second one, that is x square del 2u del x square plus 2xy del 2u del x del y plus y square del 2u del y square equals to negative of sin u plus cos 2u divided by 4 cos cube u. Okay. Now, you can see that this is that the Euler theorem, the only this part, basically the left hand side of this first thing, first equality. So, this is the Euler theorem, the left hand side part, right? And this is the Euler theorem for the second order partial derivative involved. So, this is the this part, only the left hand side part is the second order partial derivative involving that Euler theorem. Okay. So, if you directly prove this equality from this given equation, means I want to say that you find out the partial derivative of u with respect to x, then you can think that finding the partial derivative with respect to x of this function, it will take more time and it is also complicated. But by using this Euler theorem, I can easily show this equality. Okay, how? So, so before that, I require the homogeneous function. So first check, because the Euler theorem is applied for the homogeneous function only. You can check that whether u is a homogeneous function. If it is homogeneous, then you should follow this thing: u of tx comma ty should be equals to, if it is a homogeneous function, let's say of degree n, then it should be equal to t to the power n of u of x comma y. It should hold for the u, right? Now, if you put tx in the place of x and ty in the place of y, then you can check that t of xy, t of u of tx and ty, that will be sine inverse. Now you are writing tx in the place of x, and in the place of y you are writing ty, and similarly here t and t, right? Now 1 root t will be common, both numerator and denominator, and 1 root 2 will be remain, so it will be square root of this x plus y by square root of x plus square root of y. So this is not basically equal to some t to the power something to u xy, right? Because you cannot take out this root 2 outside the sine inverse. Root 2 is inside the sine inverse, and u is sine inverse of this function. So u is not a homogeneous function, but so the conclusion is that u is not the homogeneous function, so we cannot apply the Euler theorem directly on u. But you can check, if I take this function, that sin u equals to x plus y by square root of x and square root of y. If I take this function, then this new function sin z, let's say sin z equal to sin u equal to z, okay, z equal to sin u, that is a new function, that is equal to x plus y square root of divided by square root of x square root of y. This function is homogeneous, and the degree of this new function z, this degree will be half, right? Because the root 2 will be out if we put the x in the place of tx, and y tx in the place of y, ty, okay, ty in the place of y, then root 2 will be in the numerator, so degree of this homogeneous function of z will be half. Now you can apply the Euler theorem on this function z, then it will be by using the Euler theorem you will get x del z del x plus y del z del y equal to half z. Why half? Because it was n, and now n equal to half, so by using this Euler theorem I will get this one. Now z I know that is equal to sine u, right? Z equal to sine u I have taken. Then partial derivative of this function with respect to x, it will be cos u del x plus y cos u del y with respect to y equal to half, and z equal to sine z. I will put this one. Now I can take out this cos x common, both of these terms involve that cos u, and divided by cos u I will get half tan u, and this side I will get this equation. So this basically prove our first result, right? If you see that first thing we have to prove that x del u del x plus y del u del y equal to half tan u. So you can see within just a few steps I proved that this equality. So it's not very complicated. So this is one application of this Euler theorem of the first order. Now to prove that, the next one, basically this one, I have to go for that second order partial derivative of the Euler theorem, right? So I'll start with from this equation, that the last equation I talked about one. Now again I differentiate this function with respect to x. Now if I partially differentiate this function with respect to x, and this is involving of two function u and v, right? Product of two function, so it will be partial derivative like u and v method. So one constant and another derivative of the other, so x and derivative of the other one with respect to x, partial derivative, so del u del x square. Then next one, partial derivative of x with respect to x, that will be 1, so only del u del x will be there, plus y, partial derivative with respect to x, that will be del 2x del x del y, and partial derivative of y, that with respect to x it will be 0, so there is no term, and the left hand side the tan u derivative will be sec square u del u del x, right? Now we partial derivative this function with respect to y, okay, so here we differentiate with respect to x, now we do the same for the y, okay. Then okay, so before that I just change the side, so because that del u del x is there, so I can take this del u del y in the right hand side, so I'll take common del u del x, and then I'll get this equation. Then I write down this is number 2. Next I'll differentiate the first equation with respect to y, and that is similarly like uv derivative, and I'll get this equation, and again I'll take out this one in the right hand side because del u del y I'll get this. I write down this is the equation number 3. Now after that what I'll do that I multiply the number the equation number 2 with respect to x and equation number 3 with respect to y, okay. So x square, all the terms will be multiplied with x, and here all the terms will be multiplied with y, and I'll add both the terms. Then I'll get this equation, okay, and here I'll get this equation common both side, and by using the number 1 result I can put this is half of tan u, right, this one, and after that I can do little bit calculation here, that is 6 square u I multiply it with this one, so it will be 1 by 4, and 6 square is 1 by cos square u, and sin u is sin u cos u, so sin u and cos square u cos cube u minus of sin u cos u, that is tan u. After that the simplification I'll get the required result, that is negative of sin u cos u and 4 cos cube u, hence it's proved the second result. And that is the one nice application of the Euler theorem when the function is not homogeneous. So here we have taken a new function z constructed from the u such that u becomes the new function z becomes the homogeneous function, and using the result of homogeneous t of the Euler's theorem I prove that to result very easily. Okay, thank you, see you in the next lecture.